Today we're diving into something so common we rarely think about it. Switches. From the light on your wall to the network gear running the internet, switches control and direct electricity and data. In this video you'll learn what a switch really is, the core functions it performs, the many types you'll encounter, mechanical, electromechanical, solid-state, and network switches. Section 1. What is a switch? Why switches matter? A switch is a device that controls the connection between electrical or electronic circuits. It either allows current or signals to flow, or it stops them. That simple ability to make, break, or route connections underlies control systems, user interfaces, power management, safety interlocks, logic circuits, and networking. Broadly, switches operate on two domains. Power switching, dealing with currents and voltages to control lights, motors, heaters, and power electronics. Signal/data switching, routing low-voltage signals, audio, video, and packets in electronic devices and computer networks. Section 2. Core functions of switches. Even though switches come in many forms, they perform some universal roles. On-off control, make or break a circuit to power an appliance or subsystem. Selection/routing, choose among multiple circuits or connect one input to multiple outputs, e.g., changeover or multi-position switches. Isolation, provide a way to disconnect equipment for safe maintenance. Protection and fault management, used with relays and breakers to disconnect faults and prevent damage. Multiplexing and signal routing. In electronics, switch networks route data and analog signals. Safety interlock, ensure machinery can't start unless guards are closed or safe conditions are met. Network forwarding. In data networks, switches forward Ethernet frames between ports to connect devices. Section 3. Key characteristics that define a switch. When you evaluate switches, consider these technical attributes: voltage and current ratings, the maximum safe electrical load. Contact configuration, hold and throw, SPSD, SPP, DPP, etc. Determine how many circuits and paths are controlled. Mechanical life versus electrical life, cycles before failure. Mechanical versus contact erosion under load. Switching speed, slow for mechanical, very fast for semiconductor switches. Contact resistance/insertion loss, important for power heating or signal attenuation. Isolation and dielectric strength, ability to withstand voltage when open. Leakage current and off-state resistance, crucial for low-power electronics. Environmental ratings, IP protection against dust/water, temperature, vibration. Bounce behavior, mechanical contacts can chatter requiring debouncing in digital systems. Safety and certification, UL, IEC, CE, or industry-specific approvals. Section 4. Mechanical switches, familiar, human interfaces. These are the everyday switches people physically operate. Toggle switches, lever-operated, common in industrial panels and older equipment. Visual, close-up of a toggle flipper. Rocker switches, modern household appliance controls, compact, durable. Push buttons, momentary and latching variants, used in control panels, elevators, keyboards. Rotary switches, selector knobs for multi-position selection, e.g., range selector in instruments. Slide switches, small PCB-mounted switches for low-power electronics. Dip switches, dual inline package switches used for hardware configuration. Microswitches/snap action switches, tactile, fast action, used in limit switches and appliances. Key switches, for secured switching, ignition, restricted controls. Reed switches, sealed glass with magnetic actuation, used for proximity detection, meter tops, and security sensors. Visual suggestions, show each type on screen with labels and a simple animation of pulls and throws. Section 5. Electromechanical relays and contactors. Remote switching. Relays and contactors let low-power circuits control high-power loads. Electromechanical relay. Coil energizes to close contacts. Used in automation, telematics, and automotive systems. Contactor. Heavy-duty relay for motors and industrial power switching, often combined with overload protection. Latching relays. Remain in position without continuous coil power. Useful for saving energy in certain logic circuits. Mercury and old-style high-current switches are mostly deprecated due to safety. Explain isolation benefits. Control circuit is galvanically isolated from the load. Visual. Relay coil energizing and moving contacts. Section 6. Solid-state switches and semiconductor switching. Semiconductor switching dominates modern electronics and power systems. Diodes, MOSFETs, BJTs, basic electronic switches for DC/DC converters, load switching, and digital logic. IGBTs, used for high voltage, high current switching in inverters and traction systems. Triacs and thyristors, SCRs used for AC power control, dimmers, and controlled rectifiers. Solid-state relays, SSRs switch loads electronically with no moving parts. Advantages include speed and longevity. Disadvantages include leakage and heat dissipation. Analog switch ICs and multiplexers route analog/digital signals on chip with low distortion. Key trade-offs: no mechanical wear and high speed versus on-state resistance, thermal dissipation, and leakage. Visual, animated MOSFET switching on a PCB. Section 7. Contact configurations and nomenclature. Understanding pole and throw. Pole equals number of circuits controlled, single pole SP, double pole DP. Throw equals number of positions each pole can connect to, single throw ST, double throw DT. Common combos: SPSD, basic single on-off. SPDT, changeover, one input, two outputs, useful for toggling between circuits. DPDT, can switch two circuits or reverse polarity, motor direction. Show diagrams. Simple wiring examples for each config: light, motor reverse, audio source selector. Section 8. Network switches, data switching. The digital domain network switches are different. They route data packets, not electrical power. Layer 2 switches. Forward Ethernet frames based on MAC addresses, fundamental for local networks. Layer 3, multi-layer switches, combine switching and IP routing, used in enterprise cores. Managed versus unmanaged. Managed switches support VLANs, QoS, monitoring, and security. Unmanaged are plug-and-play. Section 9. Specialized and safety switches, safety interlocks, and emergency stops. Safety-rated switches with redundancy and force-guided contacts to meet standards. ISO 13849. Proximity sensors and solid-state safety switches, non-contact solutions for hazardous environments. Time delay, latching, and sequence control switches, used in complex control logic. High voltage and high current disconnects. Fused isolators, load break switches for electrical distribution. Section 10. Selection criteria and application examples. How to pick a switch. Define the load, voltage, continuous, and inrush current, inductive versus resistive. Environment, IP rating, temperature, vibration, corrosives. Duty cycle and expected life. Choose mechanical or solid state accordingly. Safety and certification, UL/IEC approvals where required. Control interface, manual, PLC-driven, or microcontroller. Examples: home light SPSD rocker, rated for mains voltage. Motor starter contactor plus overload relay, DPDT, for reversing. Microcontroller controlled LED matrix MOSFETs or transistor arrays. Office network managed post switch for VoIP phones and APs. Section 11. Common failure modes and troubleshooting. Contact wear, pitting, and welding from arcing, typical in high current mechanical switches. Coil or driver failures in relays/contactor. Semiconductor overstress causing MOSFET/IGBT short or open. Environmental ingress causing corrosion or shorts. Bounce and intermittent contact causing unreliable logic signals. Troubleshooting steps: visual inspection, continuity checks, measure coil voltage, test under load, check driver signals, and verify thermal conditions. Section 12. Safety practices and standards. Use correct rated switches for voltage and current. Size for inrush and inductive loads. Provide proper fusing and protective devices. Enclosures and IP ratings for outdoor or wet environments. Follow local electrical codes for panel wiring and safety interlocks. Use safety-rated, redundant designs for life-critical or hazardous systems. Section 13. Trends and future of switching. Solid-state switching continues to replace mechanical contacts in many domains. Faster, more reliable, programmable. Power semiconductor advances, enable higher efficiency and higher frequency switching in power electronics. Smart switches and IoT-enabled hardware, remote status, metering, and control integrated into building systems. Software-defined switching in networks, SDN, separates control plane from data plane for flexible network orchestration. Energy-efficient and secure designs in safety-critical applications and EV infrastructure. Conclusion: 1800-hour switches are deceptively simple, yet fundamental components across electrical and digital systems. Choosing the right type, mechanical, electromechanical, solid-state, or network switch, depends on the application's electrical characteristics, environmental needs, life cycle expectations, and safety requirements. In short, use mechanical switches for human interfaces and simple isolation. Use relays/contactors for remote control of high-power loads. Use solid-state switches for high-speed, high-cycle, or precision control. Use managed network switches for secure, scalable data networks. Call to action: if you found this useful, like, subscribe, and drop a comment. Which type of switch do you encounter most in your daily life? A light switch or a Wi-Fi router? Want a deep dive video on relays, MOSFETs, or PO networks? Let me know and I'll make it next. If you enjoyed this video, don't forget to like, subscribe, follow, and hit the notification bell for more tech deep dives like this. Until next time, stay curious and keep exploring. This Tech in Minute.